Okay. So these are all previous year questions. So let's go through them one by one. So this is the first question. A reservoir has a surface area of 10 kilometers square with a water surface elevation of initial water surface elevation of 182.527 meters above the mean sea level at a certain time. A precipitation event has occurred for the next 4 hours with a uniform intensity of 5 mm per hour, and the evaporation rate during this period was estimated to be 0.2 mm per hour, and during the same time there is a inflow to this reservoir of 20 meter cube per second, and there is also some outflow from the reservoir which has a value of 25 meter cube per second. At the end of the precipitation event, the reservoir level is measured to be as 182.538 meters. So we need to calculate what is the volume of water that is seeping through the ground during this time. So this is a water budget problem. So we just have to do some simple mass balance. So the water budget for the reservoir is written as precipitation plus inflow minus your outflow from the reservoir plus evaporation that is happening plus the ground seepage that happens to the ground, which should be equal to your change in storage. Okay. Now the surface area of the reservoir is given as 10 kilometers square. Which can be written as 10 power 7 meter square. Since we need our final answer in terms of volumetric unit, we'll convert all the terms in this mass balance equation into volumetric terms. So the precipitation is 5 mm per hour. And it happens for a duration of 4 hours. So the total depth of precipitation is 20 mm. And we are going to convert this into volumetric terms. So P is equal to 20 into 10 power minus 3 into 10 power 7 meter square. Next is your evaporation term. Evaporation is given as 0.2 mm per hour, and this also happens for 4 hours. So your evaporation in the volumetric term is this much meter cube. And next is your inflow to reservoir. It is given as 20 meter cube per second. So now can someone tell me what is the duration that is to be considered to convert this into volume? Hello?
Yes, sir.
So, what is the duration that you will consider to convert this inflow into a volumetric unit? Can you tell from the question? Anyone? Okay. Your precipitation happens for 4 days, 4 hours. Your evaporation also happens for 4 hours. So ideally, this also will be for 4 hours. So 20 into 60 minutes into 1 hour happens for 4 hours. So your inflow to the reservoir is this much meter cube. Similarly, for outflow from the reservoir, is given as 25 meter cube per second. So your outflow from the reservoir is 25 into 60 into 60 into for 4 hours. So next is so we have computed precipitation, inflow, outflow, evaporation. So this is the term which we need to find, and delta S is the change in the storage. So change in storage is given by your final level minus initial level. So final level in meter cube, it is 182.527 meters multiplied by the surface area of the reservoir, which is 10 kilometer square. So it is this much meter cube, and initial level 182.538 into your surface area of the reservoir. So now we can apply this equation. Precipitation plus inflow minus outflow from the reservoir plus evaporation plus seepage to the ground equal to final level minus initial level. So precipitation is 20 into 10 power 4 plus inflow to the reservoir is 288,000 minus outflow from the reservoir is 360,000 plus this is 0.8 into 10 power 4 plus your CPS to the ground, which is equal to 539. Sorry, this is so when you simplify this, this works out to be 10,000 meter cube. So this is the CPS that is happening into your ground. So any doubts in this? Hello?
Yes, sir. Yes, sir.
Okay. We'll move on to the next question. So this is a question related to your terminal velocity. So the question is, an air current moving vertically upward at 5 meter cube per second carries raindrops of various sizes. So now can someone tell me what is the significance of this data? Whether it is, whether we'll be using somewhere in the calculation? So in discussion forum, somebody has asked, vertical air velocity is given, but we don't know where to use it. So can anyone tell where can we use it and how can we use it? Just think and tell. Don't worry if it is correct or wrong. That's not an issue. Just tell what you are thinking.
Sir, vertical.
Yeah. Yes, somebody wanted to tell something. You can tell in any language if you are hesitant to speak. Okay. I'll tell you the significance of this data when we complete the this problem. So the rest of the question is, so the density of the water is given, so which is 998 kilogram per meter cube, and density of air is also given, 1.2 kg per meter cube. Now we need to calculate the terminal velocity of the 2 mm diameter droplet. And in the last part of the question, it is mentioned that if the drop is rising, we have to put negative sign for the velocity, and if it is falling, we have to use positive sign. So before that, what is terminal velocity? Can someone define? Can anyone define what is terminal velocity? So at least by seeing this figure, you should be able to say. Okay. So when we release a droplet of water from rest and it starts falling down, initially it will start accelerating, and it will keep accelerating until to a certain point when the weight of the droplet is balanced by the buoyancy force. The buoyancy force is due to the air. Okay, so let's say we have a droplet, and there are 3 different types of forces which is acting on it. So first is the Fg, which is the force due to the gravity, and it comes because of the weight of the droplet. The second force is the buoyancy force, which is a resisting force because of the air. And the third force is also a resisting force, and it's a frictional force which happens along the surface of the droplet. It's called as the frictional drag force, which is represented by Fd. And your droplet is falling with a velocity v. So first is the gravity force. So your gravity force is given by your basically your weight into acceleration due to gravity. F is equal to mg. So we need to compute the mass. Mass is given by density into volume. So here, since it is the since it relates to the weight of the water droplet, we are using the density of water multiplied by volume. This is the volume of sphere. So it is represented by pi d cube by 6, and acceleration due to gravity. Next force is the buoyancy force. It is the weight of the fluid that is displaced by the raindrop. And here we have density of air multiplied by the volume of the sphere multiplied by your acceleration due to gravity. And the last one is the friction drag force. This is a very common expression. You would have studied in your fluid mechanics also. Frictional drag force is represented as half CD into density of air multiplied by your cross-sectional area and multiplied by the fall velocity. Note that this is not terminal velocity, this is just fall velocity. And here area represents the cross-sectional area of the droplet. If you cut a sphere, you will have a circular cross-sectional area. So it is represented as pi d square by 4. So now the droplet is released from the rest and it accelerates until it reaches the terminal velocity. So at the terminal velocity, what happens is that all the 3 forces are balanced by each other. So if you write a force balance, so we are considering downward to be negative and upward to be positive. Okay. So if we write a force balance, it will be FB minus Fg plus Fd should be equal to 0, which can be represented as Fb plus Fd is equal to Fg. So this is your force balance. So that is what I have written here. Fg is equal to Fd plus Fb. And we need to find out this velocity. So when it reaches the terminal velocity, this fall velocity becomes the terminal velocity. So if I just substitute the expressions, so your drag force is represented by half CD rho A, and here you can see the fall velocity becomes the terminal velocity. And Fg is your gravity force. I am just substituting the expression and I am cancelling out the common terms, and we need Vt. Vt is given by 4 by 3 Gd divided by coefficient of drag into density of air and multiplied by this density expression, and we need to take the square root of that. Now here coefficient of drag is basically a function of your diameter, and several experiments were performed, and the coefficient of drag is basically found for different diameter of the droplets, and the values are taken from again table 3.3.1 applied hydrology by Ventichel. So here you can see for different diameters you have the coefficient of drag. So currently our diameter of the particle is 2, so our coefficient of drag is 0.517, and if we plot the diameter of the particle and your terminal velocity, you will get a curve like this. So in this you can see, even as the diameter increases, after a certain point your terminal velocity starts to flatten out. So this is a phenomenon that is observed. Suppose here if you want to find out the coefficient of drag for the droplets which are less than 0.1 mm, then what you will do? So for diameters less than 0.1 mm, so these are very tiny droplets which are present inside the clouds. So they are not yet completely grown. They are still very small. But in case if you want to find out the coefficient of drag for such kind of sizes, it is done by using the Stokes law, and the coefficient of drag is given by 24 by Reynolds number, and your Reynolds number is given by density of air multiplied by your velocity droplet size divided by mu A, which is the viscosity of air. Clear?
Yes, sir.
Yes, sir.
Yeah. Okay. Now we can solve this. So velocity of upward air current is given as 5 meters per second. We are just noting it down. Density of water is 998 kg per meter cube, and your density of air is 1.2 kg per meter cube, and diameter is 2 mm, and coefficient of drag we took out from this table as 0.517. So it is just a direct substitution. So it is 4 by 3 Gd by CD rho A square root of that. So make sure you substitute in the consistent units. So if you see, it works out to be 5.69 meters per second. Now, how will you determine this droplet is falling or rising? That is why they have given this upward air current. So if your upward air current velocity is more than your terminal velocity, it means that your droplet is not falling, it is actually rising. So for droplet to fall, your terminal velocity should be greater than your velocity of the upward air current. So here your upward air current is 5 meter cube per second. So Vt is greater than upward air current. So the droplet is falling, and if it is falling, we have to give a positive sign for the velocity. Understood? Any doubts in this? So in this table, if suppose you want to find out the coefficient of drag for 2.5 mm, you can directly interpolate between these two values, and you can get the CD for diameter equal to 2.5 mm. Okay.
Yes, sir.
Yes, sir.
Okay, we'll go to the next question. So here the question is, if the air temperature is 15 degrees centigrade, the relative humidity is 35%, atmospheric pressure is given as 101.3 kilopascals, that is your gas constant is given as 289 joule per kg Kelvin. So we need to calculate saturated vapor pressure, specific humidity and air density. So can someone tell me what is saturated vapor pressure? Have you listened to the lectures? Anyone? What is the definition of saturated vapor pressure?
No, sir.
Okay. So saturated vapor pressure is denoted by small e with a suffix x. This represents for a given air temperature there is a maximum value of moisture that air can hold. This is the most simplest definition. So for a given temperature, our air mass can hold a certain value of moisture content, and that pressure exerted by this air mass is known as the vapor pressure. Then, so we'll calculate the saturated vapor pressure. It is given by this expression 0.611 exponential 17.27 into temperature of air divided by 237.3 plus temperature of air, and you will get saturation vapor pressure in kilopascals. Okay. So here air temperature is given as 15 degrees centigrade. And here temperature of air is in degree centigrades only. This gives you a saturation vapor pressure as 1.705 kilopascals. Okay. Next is your vapor pressure. So, what is vapor pressure? It is represented by the letter E, and it represents the vapor pressure which corresponds to existing or present level of moisture in the atmosphere. So here the air is not saturated, but it is just the present amount of moisture, and the vapor pressure which is exerted at this moisture level is known as your is represented by this value. So to calculate this, we have been provided with relative humidity. So relative humidity is given as 35%. So can someone tell me the expression for relative humidity?
Sir, ratio of the vapor pressure and saturation vapor pressure.
Yeah, correct. So it is represented by RH, which is equal to ratio of vapor pressure by saturated vapor pressure. So from this we can calculate the vapor pressure as ES into relative humidity. E is equal to 1.705 into relative humidity was 35%. So this works out to be 0.597 kilopascals. Okay, next is your specific humidity. So what is the definition of specific humidity, anyone? It is represented by Q suffix V. So the actual definition of specific humidity is QV is equal to ratio of density of water vapor to the density of moisture. Which is represented by rho V and this is represented by rho U. So here we have one difficulty. We don't know what is rho V. So how do we estimate that? So everyone here knows Dalton's law, right?
Yes, sir.
Yes, sir.
Okay. So your vapor is a mixture of gases. Your air is a mixture of different gases. But by Dalton's law, we know that the partial pressure exerted by each of the gas is independent, right?
Yes.
Yes.
So we make use of that expression. So let me denote total pressure as P, and we will estimate the pressure of dry air. And we will also make use of the ideal gas law. Pressure exerted by dry air. So I am removing the vapor pressure of the moisture from this expression, which gives me the remaining quantity. So here rho A is the density of air. It can be written as your density of the dry air plus the density of vapor. And we are going to determine the pressure. Pressure is equal to your vapor pressure plus rho d Rd into T. And by the ideal gas law, we can get the expression for E as rho V into Rd divided by 0.622 into T. So this 0.622 represents the molecular weight of your water vapor divided by the molecular weight of dry air. So this 0.62 comes from ratio of molecular weight of vapor divided by molecular weight of dry air. So substituting the value for E in this particular equation, so we take out the common terms. Now what we are going to do is to get the derivation for specific humidity. I am going to take the ratio of your vapor pressure to the total pressure. This will give me okay. Now cancelling out the common terms. So now I am bringing this to the left hand side. Okay. Now this term does not is a very small value and we can neglect it. So if I neglect this, I'll be getting rho v by rho d, which is equal to 0.622 into E by P. So if you see the definition of specific humidity, it is rho v by this is rho. So this put together is into E divided by P, and your specific humidity has an expression E by P. So we know what is the vapor pressure and we know what is the total pressure that is given. So now we can compute the specific humidity. So your atmospheric pressure is given as 101.3 kilopascals. And we found the saturation vapor pressure to be, your vapor pressure is 0.597. So your specific humidity is it has a unit of kg of water per kg of moist air. And the last one is the air density. So for air density, we have the expression from the ideal gas law. But here your temperature is in Kelvin. So your air density is given by this is 289 multiplied by 273 plus 50. So your air density works out to be 1.217 kg per meter cube. Understood? Okay. Let's move to the final question. This is a little bit lengthy question. So in a 10 kilometer, and this is related to your depth of precipitable water. In a 10 kilometer high saturated atmospheric column, which is 3 meter above 3 meter square of ground, the surface conditions are given. So your air temperature is 20 degrees centigrade, your atmospheric pressure is given as 101.3 kilopascals, then your gas constant for the air is given as 287, your lapse rate is given, your density of water is also given. So here we need to find out what is the total precipitable water that is present in this column. So if you take a column, this is the atmospheric column which we are talking about, and the total height is 10 kilometer. So and it is over an area of 3 meter square. So we need to find out in this atmospheric column what is the total depth of water that is available for precipitation. So what we will do is we will take a strip by strip. So this is a small strip represented by delta Z, and we'll find out what is the mass of water that is available in each of the strip, integrated together, and then determine the depth in mm. So for that we need to fix the delta Z. So delta Z is dependent on your accuracy, so the smaller the better. So this is a 10 kilometer column, and I am going to assume a strip of 2.5 kilometers. Now, as we move from the ground level to the upper levels, your temperature decreases, your pressure also decreases, your air density decreases, your vapor pressure also decreases, and specific humidity also decreases. Now we are provided with the information of the ground only. Now we need to determine what are the parameters at each of the delta Z which we are going to consider. So for that I am going to draw a table. So this is Z in kilometers. And I am going to find out temperature in degrees centigrade, temperature in Kelvin, then pressure in kilopascals, density of air, this is in kg per meter cube, your vapor pressure, which is in kilopascals, your specific humidity, which will come in 10 power minus 3 terms. Now let me write down the ground conditions. Given us 20 degrees centigrade, pressure is given us 101.3 kilopascals, RA is given us 287 joule per kg Kelvin, and your lapse rate is given 6.5 degrees centigrade drop in temperature per kilometer rise. This is your alpha. So first step is to calculate the temperature in degrees centigrade for every delta Z which you have considered. So I am going to do a sample calculation. First one is the temperature at Z kilometers. So temperature at any Z kilometer is given by temperature at the ground minus your lapse rate multiplied by the distance from the ground. So if I'm going to compute for 2.5 kilometer height, so temperature at 2.5 is equal to your ground temperature minus 6.5 into 2.5. So temperature at 2.5 is 3.75 degrees centigrade. So now we need to compute it in Kelvin also. (273 plus 3.75), which is equal to 276.75 Kelvin. So this is the first step. Similarly, repeat for all the delta Z heights. So I have already computed, and I'll just write it down. So next we need to compute the pressure. So your pressure also changes with altitude, and in the lectures, ma'am would have derived a expression like this: pressure at any height Z is equal to pressure at your ground multiplied by temperature at the Z height divided by temperature at the ground to the power G divided by RA into alpha. So here you need to be a little bit careful. So here we need to represent alpha in terms of degree centigrade drop per meters, because your pressure is in kilopascals and it is in meter square, but if you see the alpha unit, it is given as 6.5 degree centigrade per kilometer. So here you have to convert this alpha unit. So at 2.5 kilometer height, your ground pressure is 101.3 kilopascals, and this temperature is in Kelvin. Anyway, we are going to take the ratio, so it does not matter. 276.75. Into 6.5 divided by 1000. So pressure at 2.5 kilometer height is 75.04 kilopascals. So similarly, you have to compute for all your depths. So I have already computed the depth for all the depths. So it is 101.3, 75.04, 54.59. This is 38.99, 27.09. So next term what we need to compute is your density of air. So your density of air is given by the expression rho A is equal to pressure at the height Z which you are considering divided by your gas constant for air into temperature at that particular height, and this temperature is in Kelvin. So at again 2.5 kilometers, you have density of air as 75.04 into gas constant is 287 into temperature of the air at that temperature is so similarly we have to compute for all the depths. So next we need to compute the vapor pressure. So we need to make use of the same expression which we used in the previous problem, which is 0.611 into exponential of 17.27 into temperature of the air divided by 237.3 plus temperature of air. So this gives you in kilopascals. So at 2.5 kilometers, temperature of the air is 3.75 degrees centigrade, and this is in degree centigrade. So your saturation vapor pressure is 0.799 kilopascals. Similarly, you have to compute for all the depths. So next term is your specific humidity. So your specific humidity is given by the expression 0.622 into your vapor pressure divided by the atmospheric, the total pressure. Your vapor pressure at 2.5 kilometers, 0.799. Your total pressure is 75.04. So your specific humidity is 6.622 into 10 power minus 3 kg of water per kg of moisture. So similarly you have to compute for all the depths. So everyone understood until this point? Hello.
Sir.
Yeah. Now we have computed all the terms that is necessary to calculate the mass of moisture that is present in the column. So next step is to compute the mass of the moisture. So to compute this, so I am using delta mz, which represents the incremental mass. So if you see, we are going from one level to the next level, and each level has its own specific humidity and density of air. Now to compute this, in actual senses, we need to integrate throughout the stratum. But by doing integration or by approximation, it will not give you much difference. So what we are going to do here is, we are just going to take the average value, your average value of the specific humidity, and the average value of the density of air. So your mass is given by the product of average specific humidity, average density multiplied by the volume. So here volume is your surface area multiplied by the incremental depth which you are considering. this expression will give you the mass of moisture in the strip delta Z. So if I compute between 0 kilometers and 2.5 kilometers, delta M is given by so this is here average of specific humidity multiplied by so this is average of the density of air, and your ground area is given as 3 meters square into delta Z. I am considering delta Z to be 2.5 kilometers, so I am converting it into meters. So this works out to be 84.584 kgs. So in a similar way, we need to compute for all the depths. So your specific humidity average will be so everything multiplied by 10 power minus 3. And we need to take the sum of all the masses, which will give you the total mass of moisture that is available for precipitation in that particular column. So in this you can note in the top 0 to 5 kilometers, this portion has the maximum amount of moisture. And this will be true in all the cases. Only your top few portions of your atmosphere will have the maximum amount of the moisture. So now we need to compute the depth. So this is given by summation of mass divided by density of water into area. This will be in terms of meters. So if we do 124.447 divided by 1000 into 3, this works out to be 0.0414 meters, and if I convert to mm, (41.4 millimeters). So from 0 to 10 kilometers of column, you only have 41.4 mm of water that is available for precipitation. Any doubts? Hello.
Yes.
Okay. Anyone has any other doubts related to the week 1 and week 2? Any help with the assignments which are given? Hello.
Sir, in surface water का residue time, how we calculate?
How we calculate surface water's residence time? Okay. So you can see my screen, right?
Yes.
Yes, sir.
So for surface water, for residence time, what we need in the numerator, we need the volume of water, and in the denominator, we need to know the what is the flux. That is how much kilometer cube that is getting changed from one phase to that goes from one phase to another in a year. So if you see here, so your surface water has rivers, and its volume is this much kilometer cube. And here if you see your runoff to the ocean, so it is going from one phase to the other phase. So it is this much kilometer cube per year. So if you take the ratio of these two, you will get what is the residence time of the water in the river. Understood? Any other doubts? Okay, if you have no further doubts, then I think we can close the session. So, whatever I have written in my for problem solving, which I have written, everything will be made available to you through a Google Drive link,
Okay, sir.
and presentation will also be available. The video also will be posted in YouTube. That link will be shared by you by the coordinators.
Okay, sir.
Okay, we'll meet in the next session.
Okay. Thank you, sir.